We have a wonderful guest, Mr. Stevenson, joining us again, and he is going to be telling us all about the Big Bang Theory. I have a couple questions for you, and I love all your stories, and I'd love you to share some of your wonderful stories about cosmology and astronomy. But I have some more specific questions.
Okay,
so
go ahead with that.
Can you tell us very briefly, sort of, I know it's kind of a hard concept to sum up, but what is the Big Bang Theory, and can you tell us the wonderful story about how it came to be called the Big Bang Theory?
I always like to think of the Big Bang in regard to science. Really, there are two main theories in science that seem to attract a lot of discussion, debate. In fact, leaning towards it really isn't a thing, it's more of a belief. And people say, do you believe in the science of the Big Bang Theory, or do you believe in the theory of evolution? And evolution and the Big Bang Theory, unfortunately, are really mired in debate because people don't want to believe it. But first of all, I would say, I think the reason people don't want to believe in the Big Bang Theory, and it's not a belief system, is because they don't fully understand it. They don't really know what it is. And I get that. I totally understand that, because to say that there was a large explosion that resulted in the structure and the order and the harmony of the planets, this gravitational waltz that these bodies take part in, seems like it couldn't emerge from an explosion. When I think of an explosion in a stick of dynamite, I picture destruction, a breakdown, moving to a state of maximum entropy, which is a state of disorder. How could an explosion result in order, not disorder? Mm-hmm. So I get why it's a hard thing to understand, but don't dismiss it just because you don't understand it. That would be my first piece of advice, is learn what the theory is first. Back in let's say the early part of the 1900s, the main theory that everybody subscribed to was the steady state theory, mm-hmm. And even Einstein was a strong proponent of the steady state theory, which was that the universe always has been. There really was no beginning. And there's nothing in nature that is like that. Nothing in nature is there without a beginning. Everything has a cause. So the issue of first cause flies wildly in the face of the Big Bang theory, of the steady state theory, because nothing seemed to cause it. It just always was. So, however, what do they have to go by? It seemed to be limitless. It seemed to have no edge. It seemed to go on forever. So why would we think anything other than it's always been there? Well, what ended up happening was, through maybe 100 years, through the 1800s and into the 90s, people were starting to discover things about science. It was on the heels of the scientific revolution, and a train whistle or a bell on a train, as it approaches the train station, the sound changes pitch. It goes from a high pitch as it approaches me to a lower pitch as it goes away from me. Ding, 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 right? And that was called the Doppler Effect. And it was always understood to apply to sound, but it was never thought to apply to light. Then, around the 1870s, they started to realize that there's an unusual characteristic of the elements. Hydrogen, helium, beryllium, boron, carbon, they all had their own sort of spectral signature, some sort of it's like a fingerprint, that when you burned or heated it, it would glow a particular color, but then as well, it would emit very specific wavelengths of light if you looked at it through a spectroscope. And so I could identify elements by their spectral signature. And this was sort of a revolutionary thing. And so it became that they are able to identify the elements based on this. And so, for example, somebody like Niels Bohr, the Bohr model, right? How did he figure out that the elements were in these energy levels? Where did this quantum world come from? Well, because they saw this spectrum of hydrogen and realized that it must be something to do with the electrons moving from energy level to energy level. And as it rises, it gains that energy, and as it falls, it loses it in the form of a photon, and that photon represents a specific color. So the Bohr model revolutionized our understanding of the atom. This was all happening around the same time. And then came the astronomers who said, well, does this apply to the light of the stars? Well, let's see. So with some very careful finagling and some pretty decent equipment, like you go back to the early 1900s, some of the best telescopes emerged in the early 1900s. In Victoria, just north of Victoria, there's an observatory, and the mirror is, I think, about 96 inches in diameter. There was no road leading up to the top of the hill that this thing was built on over 100 years ago. They had to pull it up. In fact, the mirror at that telescope was manufactured in Pennsylvania, was transported across the continent on train, and then placed on a cart, and horses pulled it up very carefully. And they had to fill in potholes and remove dirts and rocks so that this thing wouldn't jiggle too much, and they pulled it very slowly all the way up to the top. So in other words, don't ever say, oh, they didn't have the technology back then. Yes, they did. They were very, very good at this sort of thing. And the best telescope in the world at the time, so this is in the early 1900s, was found at the Mount Wilson Observatory in Los Angeles, California. Well, there happened to be an astronomer who worked at that observatory, and his name was Edwin Hubble. And Hubble had this idea that he would look at these objects in the sky that didn't seem to have any description. It wasn't a planet, it wasn't a star, but it seemed to be a source of light. So what was that source of light? So he set out to find out. They were up till then just called white nebulae. Well, it turns out that through careful analysis, Hubble figured out that they're actually galaxies way off on their own. So what he notices about that is that the spectrum of color from those galaxies matched perfectly with hydrogen. And so he said, aha, not only do I know what the stars are made of, but I also know that they're moving, because where the lines were supposed to be, if they were supposed to be right here, they were actually found right here. Did you catch that? Just a slight shift from where they should be to where they actually were, which was a red shift. They were shifted towards the long end of the spectrum. Red is a longer wavelength, blue is a shorter wavelength. He said, well, does it mean then that the Doppler effect applies not just to sound, but also to light? And so he realized that probably it does, and the shift to the longer wavelength is an indication that the light source was moving away. And so he actually analyzed about 50 of these things, 50 of these white nebulae, which he eventually called galaxies. And these galaxies were all red-shifted, meant they were all moving away. Well, that means then that yesterday they were all closer together than they are today. If they're constantly moving, they're constantly getting farther. So 100 years ago, 1,000, 1 million, what about 1 billion years ago? They would have been closer and closer and closer. So he hypothesized, was there ever a time when they were kind of right on top of each other? And when they calculated this, he estimated, based on what became known as Hubble's law, he graphed distance versus velocity, and he was able to calculate the velocity based on the amount of red shift. The more red shifted, the faster they seemed to be going. And as well, the further away they were, they seemed to be going faster as well. So, of course, that completely ignores the fact that he had to figure out a way to determine how far away they are. I don't even want to get into that right now, but he had to come up with a way to do that, and he did. Okay, so he plotted distance versus velocity, and he found to be a straight line correlation. If you're far, you're fast. If you're close, you're slow. But you're all moving away. So at what point, if you rewound the tape, were they all together on top of each other? Well, he estimated somewhere around 15 billion years. And there are other people who got involved in this, a fellow by the name of George Lemaitre, who actually took Einstein's work and Hubble's work and put it all together and said there seems to have been a beginning. Then, of course, others said this is ridiculous. The universe can't be doing this. Even Einstein rejected Edwin Hubble's findings. So by the late 1930s, there was an opposition, the steady state theorists versus the expanding universe theorists. Who was right? Well, at the time, there was a very outspoken steady state theorist named Fred Hoyle. And they asked him on the radio, well, what do you think of this new theory being put forth? He said, well, I think it's ridiculous. They don't even have a name for it. What are they going to do? Call it the Big Bang Theory? And of course, that stuck. They said, that is not a bad name. The problem is, if you don't really study it, what'll happen is Big Bang implies kaboom, right? So now what you're doing right now is you're picturing a vast universe empty and devoid of anything. No planets, no galaxies. It's just this maybe stick of dynamite floating in the middle of space. And all of a sudden it goes kaboom! And the universe is formed. But that's an incorrect way of thinking of it. Don't picture the universe being empty, in which there was a massive explosion that filled it with dust and debris that became the galaxies and the stars and the planets. That's really an incorrect way of thinking of it. To really consider the Big Bang Theory, think of it more like an inflation. The universe wasn't formed by being filled with an explosion. Think of it as an inflation. And the inflation created space. It didn't fill space. Mm-hmm. And as a result, that space is now expanding at the periphery at over the speed of light. So this is one aspect of the speed of light that can be broken. The universe at the very edge from where we can observe here on Earth, it seems to be traveling and expanding at a rate that is in excess of the speed of light.